of t is equal to a into x of t plus b. A into x of t is nothing but a scaling. It is related to scaling, amplitude scaling, and plus b is nothing but amplitude shifting. It can be shifted by b units, and it can be scaled by a positive. Here, a and b are real numbers. Equivalently, the above transformation can be expressed as y of t equal to a. If you take a as a common in this expression, a into x of t plus b by a into x of t plus b by a. Here the first amplitude scaling x by a, and then amplitude shifting the resulting signal by b, or first amplitude shifting x by b by a, and then amplitude scaling the resultant signal by a. It can either be expressed as amplitude shifting and scaling. Next, symmetry and addition or multiplication. Sums involving even and odd functions have the following properties. The sum of two even functions is even. The sum of two odd functions is odd. The sum of an even function and odd function is neither even nor odd, provided that neither of the functions is identically zero. That is, the sum of functions with the same type of symmetry also has the same type of symmetry. Products involving even and odd functions have the following properties. The product of two even functions is even. Similarly, the product of two odd functions is odd into odd even. The product of an even function and odd function is odd. So sum is even plus even, it is even. Odd plus odd, it is odd. Even function and odd function, even function plus odd function is neither even nor odd function. Similarly, product is even into even, even. Odd into odd, even. Even into odd, odd. That is, the product of functions with the same type of symmetry is even, while the product of functions with opposite types of symmetry is odd. Then decomposition of a signal into even and odd parts. Even function x has a unique representation of the form x of t is equal to xc of t plus xo of t. This is even part of the signal and odd part of the signal. This is the combination of even part and odd part. The total signal, the entire signal x of t can be expressed as a combination of even signal and odd signal, where the functions xc and xo are even and odd respectively. In particular, the functions xc and xo are given by xc of t equal to half of the combination of x of t and x of minus t. Here x of t is the original signal. X of minus t is nothing but its mirror image or its reflected image, reflected function. And x naught of t, xo of t is equal to half of x of t minus x of minus t. Here the mirror image can be subtracted from its original image, and it can be halved. Similarly, the even function can be expressed as the mirror image and odd image can be added and it can be halved. The functions xc and xo are called the even part and odd part of x respectively. For convenience, the even and odd parts of x are often denoted as even of x and odd of x respectively. Sum of periodic functions. Suppose x1 and x2. If we take x1 and x2 are the periodic functions, then if you want to add these two functions, x1 plus x2. So let us take two functions x1 and x2. Let x1 and x2 be periodic functions with fundamental periods t1 and t2 respectively. Then the sum y equal to x1 plus x2 is a periodic function if and only if the ratio t1 by t2 is a rational number. What is meant by rational number? That is the quotient of two integers. Rational number means quotient of two integers. Suppose T1 by T2 is equal to Q by R, where Q and R are integers and co-prime, that is these are having no common factors. Then the fundamental period Y is R into T1, R equivalently Q into T2, since RT1 is equal to QT2 by By taking the cross multiplication of this expression t1 by tt equal to q by r, then it will become rt1 is equal to qt2. So here rt1 is equal to qt2. Note that rt1 is simply the least common multiple of t1 and t2. Although the above theorem only directly addresses the case of the sum of two functions, the case of n functions where n is greater than 2 can be handled by applying the theorem repeatedly n minus 1 times. Next, coming to the right-sided signals, how these signals are right-sided, how the signals are left-sided, how these two are defined. We will see this one. A signal x is said to be right-sided if, for some finite real constant t naught, the following condition holds. It has to satisfy this condition: x of t is equal to 0 for all values of t is less than t naught. That is, x is only potentially non-zero to the right of t naught. So up to t naught, its value x of t value is 0. From t naught to infinity, it is having some value. An example of the right-sided signal is shown below. X of t is given like this. So here up to t naught, x of t value is 0. From t naught to infinity, its value is some value. So a signal x is said to be causal if x of t equal to 0 for all values of t is less than 0. A causal signal is nothing but a special case of a right-sided signal. Here, causal signal is special case of this right-sided signal. The causal signal is not to be confused with a causal system. In these two contexts, the word causal has very different meanings. Similarly, coming to the left-sided signals, like right-sided signals, we have left-sided signals also. A signal x is said to be left-sided if, for some finite real constant t naught, the following condition holds. That is, x of t is equal to 0 for all values of t is greater than t naught. That is, x is only potentially non-zero to the left of t naught. So from minus infinity to t naught, it has some value. From t naught to plus infinity, its value is 0. The example, it is the example of a left-sided signal. It will be located at the left side of the constant value t naught, real constant value t naught. Similarly, a signal x is said to be anti-causal if x of t equal to 0 for all t is greater than 0. An anti-causal system is a special case of left-sided signal, whereas a causal system is a special case of right-sided signal, as we already discussed earlier. An anti-causal system is not to be confused with an anti-causal system. In these two contexts, the word anti-causal has very different meanings. Next, finite duration and two-sided signals. Finite duration means it has some fixed time. It will be started with some fixed time and ended with some fixed time. That is some finite range. It can be represented between the finite range. So it is finite duration. So finite duration and two-sided signals can be expressed like this, or it is defined as a signal that is both left-sided and right-sided is said to be finite duration or time limited. It is nothing but time limited signal. An example of the finite duration signal is shown here. Here x of t is given like this. See, it is limited between the period t naught and t1. So it is finite duration signal. A signal that is neither left-sided nor right-sided is said to be two-sided. It is two-sided signal. It can be neither left-sided nor right-sided. So this is called two-sided signal. Whereas finite duration signal has the finite limits, finite duration. Up to certain duration only it exists. Whereas two-sided signal will exist neither right side nor left side. An example of the two-sided signal is given like this. X of t is represented like this. This is two-sided signal and this is finite duration signal. Next, coming to the bounded signals. What are bounded signals? A signal x is said to be bounded if there exists some finite positive real constant a such that mod x of t is less than or equal to a for all values of t. It has to satisfy the condition x of t is less than or equal to a for all values of t. That is, x of t is finite for all values of t. Examples of bounded signals include the sine and cosine functions. So bounded signals are nothing but sine and cosine functions. Examples of unbounded signals include the tan function and any non-constant polynomial functions. Next, power and energy signals. What is power signal and what is energy signal? Here, power signal consisting of infinite duration, whereas energy signal consisting of finite duration. So power signals, normalized power is finite and non-zero. In power signals, the normalized power is finite and non-zero, whereas in energy signals, the normalized energy is finite and non-zero. Coming to the power signals, the normalized energy averaged over infinite time is infinite, whereas in energy signal, the normalized power averaged over infinite time is zero. These power signals can be mathematically tractable, whereas these energy signals are physically realizable. This is the basic difference between the power signals and energy signals. Coming to the signal energy and power. What is signal energy? How the signal energy is defined and how the signal power is defined. There is a difference between signal energy and signal power. The energy E contained in the signal is that is represented by x, which is expressed mathematically as E equal to integral, this is integral, the integral minus infinity to infinity mod x of t whole square into dt. That energy, the signal energy can be expressed mathematically like this: E equal to integral minus infinity to infinity mod x of t whole square dt. A signal with finite energy is said to be an energy signal. So this is the definition of energy signal. How this energy signal is defined? It is nothing but a signal with finite energy. Whereas coming to the signal power, the average power P contained in the signal X is given by, which is represented by P. P is equal to limit t tends to infinity 1 by t into integral minus t by 2 to t by 2 x of t mod x of t whole square into dt. So here we are applying limit here. Limit t tends to infinity 1 by t integral minus t by 2 to t by 2 plus t by 2 mod of x of t whole square into dt. This is nothing but our signal power, average power P, which is represented by P, whereas signal energy E is represented. Signal energy is represented by E. So E is mathematically represented as minus integral minus infinity to plus infinity mod of x of t whole square into dt, whereas average power, that is denoted by P, is equal to limit t tends to infinity 1 by t into integral minus t by 2 to plus t by 2 mod x of t whole square into dt. So how the average power or signal power is defined? A signal with non-zero finite average power is said to be a power signal. A signal with finite average power or non-zero average power is said to be power signal. Whereas energy signal is defined as a signal with finite energy. Whereas a signal with a finite average power is nothing but a power signal. So this is the basic difference between energy signal and power signal. Energy signal is a signal with finite energy and power signal is a signal with finite average power. Next, coming to the elementary signals. What are the elementary signals? Or this is also named as basic signals. So, real sinusoids. First one is real sinusoids. So, real sinusoids. How the real sinusoids is defined? Real sinusoid is a continuous time signal. As we already know the difference between continuous time. What is how the continuous time signal is defined? It is continuously flowing from minus infinity to plus infinity. So real sinusoids can be defined as x of t equal to a cos omega t plus theta. A real sinusoidal or real sinusoid is a function of the form x of t equal to capital A cos omega t plus theta, where a, omega, and theta are real constants. Such a function is periodic with the fundamental period t equal to 2 pi by omega, and the fundamental frequency here omega is mod omega is fundamental frequency. A real sinusoid has a plot resembling that shown below. That it is the example for the or graphical representation of the real sinusoid a cos omega t plus theta. Next, coming to the complex exponentials. That is complex exponential. It is represented as some complex function. How the complex function is represented? E power exponential. It is represented in that manner. Exponential e power xt or e power minus xt. So these are all examples of the exponential functions. Here we have to discuss about the complex exponentials. A complex exponential is a function of the form x of t equal to a into e power lambda t, where a and lambda are complex constants. A complex exponential can exhibit one of the number of distinct modes of behavior depending on the values of its parameters capital A and lambda. These A and lambda are complex constants. For example, as special cases, complex exponentials include real exponentials and complex sinusoids. Next, coming to the unit step function. How the unit step function is defined? Unit step function. It is looking like step. So the unit step function, it is also known as a Heaviside function. Denoted denoted as u is defined as u of t is equal to 1 if t is greater than or equal to 0, or it is equal to 0 otherwise. U of t equal to 1 if t is greater than or equal to 0, or it is 0 otherwise. Due to the manner in which u is used in practice, the actual value of u of 0 is unimportant. U of 0 is unimportant. Sometimes values of 0 and 1 by 2 are also used for u of 0. So the graphical representation of u of t is represented like this. So u of t versus t. So from 0 up to it is 0 otherwise, in the sense from minus infinity to 0 its value is 0, from 0 to infinity its value is 1. So u of t equal to 1 for t is greater than or equal to 0. This is represented like this is the graphical representation of unit step function. Next, coming to the signum function. What is meant by signum function? It is combination of the unit step function and mirror image of the reflected unit step function. It is the combination of unit step function and mirror image of the reflected unit step function. So mathematically, the signum function is represented like this: signum SGN. It is denoted by SGN. SGN of t is equal to minus 1 if t is less than 0. So its value is minus 1 from minus infinity to 0, and its value is 0 at t equal to 0, and its value is 1 if t is greater than 0. From its definition, one can see that the signum function simply computes the sign of a number. So the graphical representation of signum function can be represented like this. Some minus infinity to from minus infinity to 0 its value is minus 1, and 0 to infinity its value is 1 plus 1, and at 0 its value is 0. This is the graphical representation of our signum function. Then rectangular function. Coming to the rectangular function, the rectangular function, it is also called as unit rectangular pulse function. Unit rectangular pulse function. This is denoted by RECT rect, which is given by rect of t is equal to 1 if minus 1 by 2 is less than or equal to t is less than 1 by 2, and it is equal to 0 otherwise. So it is rectangular function. It is located both positive side as well as negative side. So due to the manner in which Rect function is used in practice. The actual value of rect of t at t equal to plus or minus 1 by 2 is unimportant. Sometimes different values are used from those specified value. It is not minus 1 by 2 or plus 1 by 2. It may be minus 1 and plus 1, minus 2 and plus 2, minus 3 and plus 3, etc. But it can be located both positive side as well as negative side. So the graphical representation of the rectangular function is represented like this. So if we see here, it is located or it is represented from minus 1 by 2 to plus 1 by 2. From minus 1 by 2 to plus 1 by 2, its value is plus 1. Remaining values are 0. Next, coming to the triangular function. What is meant by triangular function? It is looking like triangle. A triangular function, it is also called the unit triangular pulse function, which is denoted by TRI, which is defined as TRI of t is equal to 1 minus 2 into mod t, where mod t is less than or equal to 1 by 2. 1 minus 2 mod t. Here mod t is less than or equal to 1 by 2, or its value is 0 otherwise. So the graphical representation of our triangular function is like this. Next, coming to the unit impulse function. The unit impulse function, it is also known as the direct delta function or delta function. The other name of unit impulse function is delta direct or Dirac delta function, or delta function denoted by delta, is defined by the following two properties. Delta of t is equal to 0 for t equal to 0. Its value is 0. Its value is 0 at t is not equal to 0. Its value is 1 at t equal to 0. Its value is 1 at t equal to 0. Or we can uh, define as minus infinity to 0 delta t of t dt is equal to 1. So technically, delta is not a function in the ordinary sense. Rather, it is what is known as generalized function. Consequently, the delta function sometimes behave in unusual ways. Graphically, the delta function is represented as shown below. Here, delta of t is represented like this. At the value of t equal to 0, its value is 1. Here, it is some delta of t minus t naught. It can be shifted towards right side by t naught, t naught units. So, at t naught, its value is some k into delta of t minus t naught. If the value of k is 1, then here here it is, if it is delta into t minus t naught, then the value of k is 1. At t naught, its value is 1. This is unit impulse function. So this is the comparison between unit step function, unit impulse function, and unit ramp function. See, unit step function in continuous time and discrete time signals, it is mathematically, unit step function is represented like this. So u of t equal to 1 for t is greater than 0, and is 0 for t is less than 0. It is 1 for t is greater than or equal to 0 in the continuous time signal manner. Whereas coming to the discrete time signal manner, u of n equal to 1 for n is greater than or equal to 0, and it is 0 for n is less than 0. This is the mathematical representation of our unit step function. Coming to the unit impulse function, delta of t, it is denoted by delta of t in continuous time. It is equal to 0 for t is not equal to 0, and it is also expressed like this: integral minus infinity to plus infinity delta of t dt is equal to integral 0 minus to 0 plus delta of t dt is equal to 1. The representation of dt, delta of t in dt discrete time signal, is delta of n is equal to 1 for n equal to 0 and equal to 0 for n is not equal to 0. Coming to the unit ramp function, r of t equal to t for t is greater than or equal to 0, and it is represented as r of t equal to 0 for t is less than 0. Here r of t is also expressed as r of t equal to t into u of t. U of t value is 1 here. Okay, u of t is nothing but d by dt of r of t. Or here r of t value is t, so d by dt of t that is equal to 1. Then RFN it is nothing but the representation of the unit ramp function in discrete time signal. So RFN equal to n for n is greater than or equal to 0, and is 0 for n is less than 0. So this is the mathematical representation of unit step, unit impulse, and unit ramp functions like this. This is the basic mathematical representation of all these signals: unit step, unit impulse, and unit ramp function. Then coming to the systems, how the system is defined. So far we discussed about the definition of signal, classification of signals, operations on signals, and the different types of basic elementary signals, elementary or basic signals, different types of basic signals, etc. Now we are going to discuss about what is system, how the system is defined, what are the classifications of systems, what are the types of the systems, what are the operations on systems, etc. Here, the system is defined as a system is an entity that processes one or more input signals in order to produce one or more output signals. So, system is something. System is something. It takes the signal as the input. It processes something, and it will give another signal as the output. Here, see this diagram. Here, this is the graphical representation of the system. Here, the system will take the n number of inputs here: x0, x1, x2, x3 up to xn. These are m number of inputs. Here, it will produce. It takes m number of input signals. It processes these m number of input signals and gives n number of output signals. Like and this is the sequence of y0, y1, y2, y3, yn, y4 up to yn. So this system is an entity that processes one or more input signals in order to produce one or more output signals. We have m number of input signals here. So system will take m number of input signals it processes, and it will give n number of output signals. That's why you can say that system is an entity that processes one or more input signals in order to produce one or more output signals. Then coming to the classification of systems, how these systems are classified based on the number of inputs. Suppose a system with one input is said to be a single input, that is Si. A system with more than one input is said to be multiple input. More than one input is multiple inputs, that is Mi. Next, coming to the based on the number of outputs, a system with one output is said to be single output, that is denoted by SO. A system with more than one output is said to be multiple output, that is MO. Then types of signals processed. A system can be classified in terms of the types of signals that is processes. Consequently, terms such as the following, which describe signals, can also be used to describe systems: one-dimensional and multidimensional systems, continuous time, that is CT, and discrete time, DT, and analog and digital. For example, a continuous time CT system processes CT signals, and a discrete time DT system processes discrete signals. We already aware of CT and DT. CT means it is a continuous time signal, whereas it is a continuous time system. Coming to the DT signal, it is not a continuous. Here, the continuous time system can be frozen for some time, and it can be divided into equal intervals of the time, so that it will become DT, DT signal or system. Next, coming to the types of systems, how these systems are classified. Here we have five types of systems are there. First one is causal and non-causal system. Second one is linear and non-linear system. Third one is time variant and time invariant system. Fourth one is stable and unstable system. And last one is static and dynamic system. What is meant by causal system? Causal system, how the causal system is defined, a system is said to be causal if the present value of the output signal depends only on the present and or past values of the input signals. Present value of the output signal depends on present and past values of the input signals. For example, y of n is the output signal. It depends on the present value. Present value of x of n is x of n plus past value of x of n is 1 by 2 into x of n minus 1. So a system is said to be causal if its output depends on output value. The present value of the output signal depends only on the present and or past value of the input signal. That is called causal system. And coming to the non-causal systems, what is meant by non-causal system? Non-causal system is a system is said to be anti-causal or non-causal if the present value of the output signal depends only on the future values of the input signal. Future values of the input signal, whereas causal system depends upon the present and past values of the input signal, whereas non-causal system depends upon the output of value of the uh, present value of the output signal depends upon the future values of the input signal. For example, y of n is the present output signal which depends upon the future values, that is x of n plus 1 plus 1 by 2 into x of n minus 1. These are all the future values of the input signal. So if the present value of the output signal depends upon the future values of the input signal, then we can say that a system is a non-causal system. Then coming to the linear and non-linear systems. What is meant by linear system? A system is said to be linear if it satisfies the principle of superposition theorem. The system is said to be linear if it satisfies the principle of superposition theorem, superposition of homogeneity. For checking the linearity of the given system, firstly we check the response due to linear combination of inputs, that is x1 of t plus x2 of t, like that. Then we combine the two outputs linearly in the same manner as the inputs are combined, and again total response is checked. So firstly we will add x1 plus x2, then the y of t equal to a into x1 of t plus b into x2 of t, like this. So this is called linear system. If it does not satisfy the principle of superposition and homogeneity, then we can say that it is non-linear system. Then next one is time invariant and time variant systems. What is meant by time invariant and what is meant by time variant? So a system is said to be time invariant if a time delay or time advance of the input signal leads to a identical time shift in the output signal, that is represented mathematically as yi of t is equal to h of x of t minus t naught. H of S T naught of x of t is equal to hs t naught of x of t. Linear time, coming to the linear time invariant systems, this is the special importance for their mathematical tractability. Most signal processing applications involve linear time invariant systems only. LTA systems can be completely characterized by their impulse response, which is represented mathematically as y of n equal to transformation of x of n, that is transformation of sigma k equal to minus infinity to infinity x of k into delta of n minus k. This is the linearity property. Whereas sigma k equal to minus infinity to infinity x of t into t of delta of n minus k is equal to sigma k equal to minus infinity to infinity x of k into hk of n. This is time invariant system. Then coming to the stable and unstable systems. What is meant by stable system? A system is said to be bounded input, bounded output stable. That is nothing but BIBO stable, bounded input, bounded output stable if every bounded input results in a bounded output that is represented by for all values of t mod x of t is less than or equal to m of mx is less than infinity tends to for all values of t mod y of t is less than or equal to mv is less than infinity. So bounded inputs and bounded outputs. So bounded inputs results in bounded outputs. Here the bounded inputs are x of t. Here mx is in between a mod x of t and infinity, whereas my is in between mod y of t and infinity. So bounded input results in bounded output. That is stable. This is about the stable and unstable systems. So, for example, the system represented by y of t equal to a into x of t is unstable, such that a is greater than 1. Here the reason is, let us assume x of t equal to u of t. Then at every instant u of t will keep on multiplying with a and hence it will not be bounded. If a is less than 1 or if a value is 0, then if a is not greater than 1, it means that a is less than 1 or a equal to 0, then it is not stable. The system is not stable. Coming to the static systems. What is meant by static system? A static system is mainly memoryless system. It does not have any memoryless system. That is called static system. It has no storage device. If memory is not there, then there is no storage device. Its output signal depends on present values of the input signal. So it doesn't have any memory, so it can't store any value. That's why it will take input and it will do the same input as the output. So output signal depends on present values of the input signal. For example, I of t equal 1 by r into v of t. This is a mathematical expression. Next, coming to the dynamic systems. So it has memory. Dynamic systems has memory. It has storage devices. So a dynamic system possesses memory. It has a storage device. A system is said to possess memory if its output signal depends on past values and future values of the input signal. That is represented mathematically as I of t equal to 1 by L integral minus infinity to plus t v of tau t tau. Then memoryless system. What is meant by memoryless system? It does not have the capability of storage or anything. So it is called memoryless system. A system is memoryless if the output y of n at every value of n depends only on the input x of n at the same value of n. There is no storage device here. That's why it can't store the previous value. That's why it output depends on the present input value only. For example, square, if we take the square, y of n equal to xn square, sine, sine y of n equal to sine of x of n. Then coming to the discrete time systems. Discrete time system. So in the next class we'll discuss about all these things. Today I am ending this session.